Flat structures are the simplest way to organize data. They represent information as a single level of fields, without nesting or hierarchical relationships. If structure is the blueprint of data, then a flat structure is a single-floor building where everything exists on the same level. In a flat data structure, each record contains values arranged side by side, typically in rows and columns. CSV files, spreadsheets, and relational database tables are the most common examples of flat structures. Each column represents a variable, and each row represents a single observation or entity. Flat structures prioritize clarity and accessibility. Because all fields exist at the same level, the representation is easy to read, query, and manipulate. There is no need to traverse nested objects or reconstruct hierarchies to access values. So what defines a flat structure technically? First, fields are scalar rather than nested. Second, relationships are implicit rather than embedded. Third, records are uniform, meaning each row follows the same schema. This uniformity makes flat structures highly compatible with analytical tools. Most statistical software, visualization tools, and machine learning pipelines expect flat, tabular data. This is why so many data workflows end with flattening transformations. Flat structures also support efficient column-based operations. Filtering, aggregation, sorting, and grouping become straightforward when variables are aligned in columns. Indexing strategies are easier to implement and reason about in flat schemas. However, simplicity comes with trade-offs. Real-world entities are rarely flat. People have multiple addresses, orders contain multiple items, and events often contain nested metadata. Representing complex relationships in flat structures requires duplication or decomposition. Sometimes nested information is flattened into repeated rows. Other times, relationships are split across multiple tables connected by keys. Both approaches introduce modeling decisions that affect correctness and performance. One common technique is normalization. Data is divided into multiple flat tables, each representing a single entity type. Relationships are then expressed using identifiers rather than nesting. Another approach is denormalization. Related values are duplicated into the same flat record to optimize read performance. This can improve speed, but increases the risk of inconsistency. Why do flat structures remain so dominant despite these limitations? Because they balance simplicity, predictability, and computational efficiency. Flat structures align well with relational algebra, vectorized computation, and columnar storage systems. They also serve as a common interchange format between systems. APIs, exports, logs, and data pipelines often convert complex data into flat representations for compatibility. Flat structures are especially important in analytics and machine learning. Feature matrices, training datasets, and reporting tables are almost always flat. Even deeply nested source data is typically flattened before modeling. Flat structures therefore act as a translation layer between complex reality and computational workflows. What are the defining strengths of flat structures? They are easy to validate, easy to serialize, and easy to index. They minimize ambiguity by enforcing uniform schemas. They are simple to inspect and debug. And what are their weaknesses? They struggle to represent hierarchy and one-to-many relationships naturally. They can obscure meaning when nested context is flattened into repeated fields. They may require expensive joins or transformations to reconstruct original relationships. Designing flat structures requires careful choices about keys, granularity, and duplication. The unit of observation must be clearly defined. Identifiers must remain stable across datasets. Relationships must be documented even when not explicitly represented. Good flat data modeling preserves meaning while simplifying representation. It ensures that flattening does not silently distort relationships or counts. When working with flat structures, analysts often become the bridge between representation and reality. They reconstruct relationships conceptually, even when the data appears simple. Flat structures are not primitive or outdated. They are foundational, They power databases, analytics platforms, and data science workflows across nearly every industry. Flat structures remind us that the goal of data modeling is not to mirror reality perfectly, but to represent it in ways computers can process reliably. When used thoughtfully, flat structures make data understandable, portable, and computationally efficient.